Okay. So on Thursday, I will be going down to the coast to teach 460, 560 from there. As for what will happen with this class, I think it'll depend on what happens today. Because my plan for this week is to finish covering everything in chapter 4. And in terms of pages of notes, that is not a lot, but it can be some pretty difficult stuff to work with in MATLAB, so I want to make sure to spend enough time on that. So I may not, so if I don't get through all of that today, then that's, so we'll just meet virtually, just like the last time I went to the coast, and handle it that way. Okay, but since I'm not under huge time pressure as far as covering stuff, I can certainly take a little time to ask you all what's going on with homework.
The idea of doing it is swirling around in my head. That's what's going on for me.
I appreciate your honesty, but you know, you did just finish a thesis, or about to.
It's getting up there on the due now list.
Okay.
The due yesterday list.
Yeah. Okay. Anyone else want to update me on what they're doing now, or did yesterday?
Number 2.
Yeah.
2C.
Mhm.
I still did not get fourth order. That second order, I really don't know what I'm doing.
I'm getting the second order for 2C as well.
Oh. Okay.
There's a very strange behavior with B.
Uh,
That's the one where the second derivative does not exist.
right.
So when I did it, I got on second order. But we discovered something weird is acting in the nice way. We change n. So at first we use n to be, say, 500, 1,000, 2,000. And we go to the second order.
And if you like change n by 1, so if you like subtract 1 from n, all of a sudden it's no longer second order.
Oh, wait, change what?
So like at first we did n to be 500, 1,000, 2,000.
Yeah. Yeah. Okay.
Then we change n to be 2 raised to the power of 7 minus 1. 2 raised to the power of 8 minus 3, and 2 raised to the power of 9 minus 1. And then we change the first order.
Ooh.
But then if we get rid of the minus 1, it goes back to second order.
Oh, okay. Interesting. Okay. I'm trying to think if there's something that would happen because of how things align on the grid. And this is part D. Okay. So one possibility could be whether it be discontinuity, like the point of discontinuity aligns with the grid or not, because well, because I mentioned earlier, it could be treated as like as a big, not really a discontinuous function, but a smooth function that happens to have a steep slope. But since there's always going to be a gap of size delta x between grid points where a function assumes one value versus another, although, but you could have grid points happening where, like, where the jump happens at a grid point or midway between grid points that could possibly affect the behavior. I don't recall offhand if that coming up in previous incarnations of this class. No. Okay. Actually, I'm looking for any old code that I have here. For example, I have some code that I whipped up a long time ago that deals with that's this implementation of the simplest part, like part 2A. Let's see. Now, so what you're saying is when it was power of 2 minus 1 versus just a power of 2.
Yeah.
And so with a minus 1.
Just first order.
Okay, but without it, it was second order. Okay. What I'm wondering here is, okay. All right, I'm playing around here with some code that I have. I want to see if it's possible to look into quickly the mystery of 2C. Okay. Okay. Where okay. Plus. Well, trying to do this on the fly might be not such a good idea. Okay. Oh. Wait, sine of 0 is 0, cosine of 0. Okay. Minus pi d, and then pi is 9 pi. Okay, so that's 0. Okay. Sorry, I'm taking time to look at various like homework handouts and all that sort of thing. Let's see, this is homework 1. Okay. 2/12 squared. Oh wait, A is second derivative. Okay, A is minus second derivative. Okay. Plus, and that should be. Okay. I'm trying to make sure that I'm not accidentally having to do something that's impossible, but I'm pretty sure it was possible. Okay. Yes. Okay. So I've confirmed that fourth order accuracy does work for problem 2C. So in other words, we had to find out what is the mistake in your code for why it's still second order. Yeah, because all it takes is one little thing off, and second order accuracy is all you're going to get. Okay, so this all boils down to the changing a right-hand side. So I'll refer to the modified right-hand side as F new is equal to the original F. And then what's added on here is squared over 12 times, and what goes in here is your approximation of the second derivative of F. Okay, so using the center difference. Now, you have a matrix that does second derivative, or a way you've written, depending on how you've written it, it may be minus second derivative. But what you have to make sure of is that it amounts to this, 1 over h squared times this matrix. Okay, applied to the original F. But because F, and I mentioned this before, but it's worth repeating, F is not 0 on the boundary. And the coefficient of boundary values will be 1 over h squared. Then you need F of 0 for the first element of this vector, this boundary correction vector, and then F of 1 for the last element. So as long as you ensure that that's what you have here. So when I was doing this just now, I had the code for the original second order scheme. And then I say, okay, well now I got to modify F. Now I have to do this. And in doing so, I will admit to have made some sign mistakes. Once I fixed them, then I noticed that the error was a lot less. So this is a thing to check. And what you have here is most likely, like if you set up your original second order scheme as, AU equals F, then this matrix right here is minus A. Which was one of my mistakes that I made just now, I might add, seeing it the first time. It's what I noticed that when I had things incorrect, and running a code for, like, let's say 1,024 grid points. So the errors in the order of like 10 to the minus 4, 10 to the minus 5, something like that. Once everything was in order, everything was fixed, the error for that many grid points went down to like 10 to the minus 8. And also decreases at a fourth order rate. So I don't know if you're spotting anything that might need to be fixed based on that. Okay. And so then I had to go back to the formula for a given f of x, sine 5x, 5 prime squared, et cetera, and work that out, or go out for x equals 0, x equals 1, and use those formulas here and here. And everything else in between is 0. Okay. Questions? Robert, you saw anything? Or?
I was waiting for MATLAB to load so I could
Oh, okay.
look at what I had.
Okay. I'll help you find that, whatever it is. Okay. Okay. Now, as for the other problem or part of a problem that we've just been discussing. Okay. Oh, you did? Okay, good. Yeah, that's what it was.
I think the error was f of 0 negative, f of 1 was.
Oh, okay. Okay, yep. That would do it. Okay. All right. Let's see. As far as part D is concerned, really, I'm just looking for you to tell me what you observe. Yeah. So because what you're doing here is, as far as the code goes, there's no deviation from what you had before, except you're just changing its right-hand side. I mean, it's certainly any odd behavior like what you're telling me about, how a change in number of grid points could lead to a significant change of behavior. And I admit that's something I had not looked at before. By all means, tell me about it. But I mean, it's not something to be concerned about as far as how I'll grade this problem. I'm just looking for you to try this out and report back. So. Okay. Other things for homework? 4. Okay. I have a spectral method, or Chebyshev one.
What did you say if you say these kind of grids?
Same kind of grid you've been using, equally spaced points.
Isn't the solution supposed to be the same, like spectral method and
Ideally, yes, but they will turn out not to be the same. Now, in the limit, as you increase the number of grid points for both, you will see both methods converge to the correct solution. The thing to look, the discrepancy you'll see is how many grid points does it take for each method before you start getting something that's at least reasonable? Because if you don't choose many grid points, your solution is going to look awful. and that's okay. You just want to make sure that as you increase, let's say n, the number of grid points, that that it starts converging. Because the thing is, if you look at the PDE, okay, all right. Minus epsilon uxx plus ux equal 1, and then boundary conditions u of minus 1 is 0. U of 1 is, also 0. Okay. But because epsilon is small, the PDE is close to simply ux equals 1. So it's a solution having a slope of 1. And certainly at the left endpoint, it'll start at 0. But then what will happen is, because of this boundary condition, there'll be a sharp drop-off back to 0 at the right side. So a solution, so it's going to be something like that. And that's a difficult solution to compute using these finite difference or spectral methods. So for a smaller number of grid points, you're not going to get that at all. But what you should see is that Chebyshev, if you compute solutions using both methods for the same number of grid points and let it keep increasing, that Chebyshev should get its act together sooner. And if you're using center difference for both uxx and ux, then theoretically your scheme, your finite difference method ought to be second order accurate. But it sure it's not going to look that way. And the first time I signed this problem, it's like, okay, I can show you guys how to compute the solution, like analytically, because this is a first order ODE in UX. So you can use like an integrating factor to solve for UX and then integrate that.
So what analytically, because I did that.
Yeah.
Well, I couldn't evaluate that as a matter.
Yes, that's the problem. Because you have exponential involving like an epsilon in the denominator. It's like it overflows or something. It's, yeah. So unfortunately, you can't evaluate error in the way that you're used to from problem 2. So that avenue's out, unfortunately. But okay. So actually, what I would want to see as far as like what you submit. I mean, you can discuss what you observe, but it'd be good to submit a few plots, like for a selection of number of grid points. Here's the solution for finite difference using n number of grid points, and then Chebyshev using the same numbers of grid points. So you can contrast the behavior of a solution.
I realize I'm doing something wrong. I just increase the number of grid points to like 1,000.
Okay. And this is finite difference?
Like I plus both solutions.
Oh yeah, okay, both methods. Okay.
U is the finite.
Okay, so the finite difference is correct. So it looks like if Chebyshev, yes, okay.
Because We still were removing the first row's first column, last row, last column, right?
Right, so after you form you minus epsilon dn squared and then plus dn, then you remove a first and last row and column of that matrix. Okay, and since we're already in the interval -1 to 1, which Chebyshev is built for.
Okay, is after we added epsilon before we remove the rows?
Okay.
You say you have to multiply by epsilon before removing the rows and column?
Oh, well, since it's just a scaling factor, that part won't matter. But the thing that I had to make sure of is you, for the minus epsilon uxx part, that you square the differentiation matrix first before you remove a first and last row and column. Okay. Now let's see if. Oh, I have someone's code for that. Okay. 4B. Oh, that's weird. Why is it not working? Oh. Okay. Let's just do this one. Oh. This is weird. Oh, I have some students' code here from old code for 4B, and it's very wrong. Okay. And if the most likely problem is yes, it's that Chebyshev's differentiation matrix is such a mess.
Because I tried writing the differential matrix. So I tried googling how to get a differential matrix. Come across a textbook. Spectral methods of PE. And they gave a function that was right.
Yeah.
And I got reading for a function could write, I would just produce a differential matrix. So that's what I did.
All right. Oh, what happened here? Okay, so I have here some working Chebyshev code. Okay. And what happens is, yeah, if n is large enough, you get the same solution as you just saw for finite difference. Not enough grid points, you get some oscillations. So, okay. But the fact that the solution.
Like what value did you use?
512. Yeah, because the fact that your solution appeared to be correct except shifted downward. Yeah. So summing up for matrix, presumably. Of course, there are a lot of opportunities for something to go wrong there. Oh. Okay. So you implement the matrix based on like what you saw in the book.
Yeah, so they give a code on how to get the matrix.
Right.
So what you just do is tell the number of grid points and produce a matrix and X value.
Okay. That is a possibility. Well, the UXX matrix, that part should be symmetric. But okay. Well, and one thing you could do is if you were to, because once you generate the temperature differentiation matrix, then it's pretty easy to work things out from there because you're squaring, including rows and columns, et cetera. One thing that if you want, if you were to generate just the first derivative matrix, Chebyshev, for like a small value of n, and then I could compare that, like you could send me that matrix, I could compare that to what's generated here and see if there's a discrepancy. Yeah. Okay. Yeah, because you're definitely close. Anyone else discuss parts problem 4? Or?
I have not started on wrong.
Okay. Now, once I cover the multigrid stuff, which is actually the very next topic coming up, that will have everybody ready to do problem 6. Problem 7 is a 2-dimensional problem, and I believe that's using finite differences. I just want to make sure I can tell you all correctly when you've seen enough material to do everything. Yeah, problem 7. Okay, it's finite difference, and there's also multigrid. So problem 6 and 7 are both about that. Okay. Let's see. X squared y. Okay. Okay. Are any of our homework questions before I resume covering stuff? Oh, okay, even better. All right. Oh, eraser cut in half.
Yes. Almost.
Oh, it's not quite there? Or?
Yeah, this is it right now.
Oh. This is really weird. Okay.
So this is it.
Yeah.
So like we agree on this point, but this one should be now, and then Chebyshev is not.
Okay. Well, really, the solution is supposed to go down. It's just that the finite difference, because of that sharp jump at the end, there's going to be some bad behavior, and Chebyshev handles that better. So yeah, looks like it's all good. Alrighty. Okay. So, all right, so suppose as before dealing with computation.
Hey, Dr. Lambers?
Yeah.
Could you like shift the screen over just a little bit?
Sorry, I forgot I moved a computer.
There you go. Thank you.
Okay, sorry about that. Okay, so Poisson's equation. All right, and so you discretize that as you have been doing in the homework, and you have a system of this form. And I'm using a subscript H to indicate the grid spacing H from your discretization and your finite differences and all that. If there was some finite difference. Just because we're going to be looking at the system for different grid sizes, hence the name multigrid. So what multigrid is about is coming up with a more efficient way of solving this system using iterative methods, like I've just been talking about, but also an understanding of how the error behaves when you're using these iterative methods. Okay. All right. So if we use an iterative method of the forms discussed last time, for example, one of the stationary iterative methods like Jacobi or Gauss-Seidel. So I'll write it in this form. Preconditioner of some kind times the difference in iterates. So I'll call this dk, as I did before, is equal to rk, the kth residual, which is going to be the right-hand side okay, and so really what we're doing is you have your previous solution, you solve this system, and then you add this dk onto uk, and it gives you uk plus 1. And the choice of a preconditioner P depends on what stationary iterative method you want to use. You might use P being the diagonal of A for Jacobi, or the lower triangle of A for Gauss-Seidel, etc. Okay. All right. Now, there's one important property of these kind of iterative methods that we want to make use of. So then the error becomes smooth. In other words, the high frequency components of the error tend to go to 0 more rapidly than the low frequency components. And the reason why this observation is very important is how we can exploit that. That we can use a grid with fewer points, or a coarser grid. And of course, having fewer grid points would mean more efficiency. So what we can do is, whatever grid we're starting out on originally that might have a lot of points, we can go ahead and use this iterative method. Let the error get smoother and smoother. And after a time, when it's smooth enough, we downsize. We go to a coarser grid and continue the iteration there. The error will get smoother still. So So as the area gets even smoother, go down to a smaller grid, and so on. Keep going until the problem is so small, because we're on a grid of very few points, then we can just go ahead and solve it whatever way we like, because it doesn't really matter at that point, because it's going to be efficient no matter what we do. So that's the main idea behind a multi-grid method, that we use the behavior of the error to solve a problem on successively smaller grids. Okay. All right. Now, so problems 6 and 7 deal with using multigrid, and it's something that students in the past have had some difficulty with, just because the way it's coded is kind of weird. Because it uses an idea that we have not discussed to this point, and it didn't come up in previous classes either, like 610, and that is the idea of recursion. All right. So what I'll do is show you exactly how, in this pseudocode, how we exploit this idea in a systematic way to be able to solve this problem more efficiently. Okay. One of my former students, PhD students, Haley Dozier, a big part of her dissertation was on a multi-grid version of my KSS methods for solving PDEs. And the idea was the same. The error got smooth, therefore we could correct the solution on a coarser grid for greater efficiency. So there are a lot of problems where this idea can be used. Anytime you have a situation where the error gets smoother and smoother, because if you have a smooth function, you don't need many grid points to represent it. You can go with a coarser grid. Okay. All right. Okay. So what we assume is we're going to solve this problem that I wrote before. AHUH is equal to FH. So I use a subscript at all times to indicate what grid we're currently working on. All right. So the first thing you do is, okay. Okay. So I have to be very careful with my notation here. Okay. right, so we're using this iterative method. All right, where Rk is equal to the right-hand side, and I'll keep using a subscript h's everywhere. We're working on the original grid at this point. And we have each new u is equal to a previous one plus the solution of this preconditioned system. And this is just how the iterative method works. And then the initial iterates, we can just use 0. So first time around, your residual, your right-hand side, is just f, because this part will be 0. You go ahead and solve this system to get using R0 on the right side, you get D0 as a solution. Add it to your initial guess of 0 to get U1. That's your first solution. So we keep using its iteration up to a certain point. All right. Now you could run this all the way to convergence, but you don't want to do that. That's not the most efficient way to go. We don't want to drive the error all the way to 0. We just want the error to be smoother than before. So the result of this is some approximate solution that is what we call UH with no superscript. And it still has error in it, but its error is smoother than before. That's all we need to accomplish here. So we might only use a few iterations, depending on what your choice of preconditioner is. And like I said, a preconditioner could be one for Jacobi or Gauss-Seidel or whatever. Like in the homework, you use Gauss-Seidel. So pH would be like a lower triangle of a matrix A.
So when you say error is smoother, what does that mean?
Like if you were to take a Fourier transform, a discrete Fourier transform of the error, that components of that transform corresponding to higher frequencies would be negligibly small. Or if you were to plot the error, it would look like a smooth function. Yeah. So what that would mean is so that's what would justify representing its error on a coarser grid. But we don't have the error at this point. We just know that that's the behavior of the error. But what we can get is a residual. We can compute that. Okay. Now, so after we carry out this iteration up to a certain point, just to get the error smoother, we might use some like predefined number of iterations. Then the next thing you do is you restrict the residual RH, which is going to be FH minus AHUH. So you go ahead and compute that residual. And any matrices involved, AH and PH, to a coarser grid of spacing 2H. So half as many grid points. So from that restriction process, you now have these vectors R2H and a matrix A2H and P2H. Now, in the case of Poisson's equation, say one dimension, your matrix A comes from the center difference for however many grid points. You know how to form that matrix. So you would just form that matrix with a different spacing. So this part would be pretty easy to do. I've not yet explained how you do this. You take a given vector and restrict it to a coarser grid. But I will explain that after I get through this part. Okay. So now that you're on a coarser grid, this is where recursion happens. We will solve the problem A2H, E2H equals R2H. Okay, so you take your restricted residual, you take your matrix that's on the coarser grid, and when I say recursion, what that means is you're going to treat this problem as the input to the same algorithm I'm describing. So you are writing a function to do all of this stuff, and when you get to this point, that function is going to call itself with these inputs. Because here the input coming in is a matrix, AH, and the right-hand side, FH. What do I have here? I have a matrix and a right-hand side. So the function will call itself. So what you're doing is you're delegating. You're saying, okay, it's really no different than calling any other function. Like if you wrote separate functions to do these things. Like you're delegating this task to that function, and then it comes back with the output, which is E2H in this case, and then you work with it. The same thing applies if a function you're delegating to is that same function. The only thing you have to make sure of is that recursion doesn't go on forever, because you have a problem coming in of a certain size. Now it's a problem of half the size, and you'll call this function will call itself. All the stuff that you have going here is still there. It doesn't go away. Whenever a function calls itself, it has its separate memory space for each time it's called. So this function will do its thing, come back at the output, and all this stuff is still there, and the first instance of a function can work with this now and continue the job, which I've yet to describe. So, so the limiting case that recursion must always have if the size of a problem that's coming in, AH, UH equals FH, is too small, then just solve it directly. Use the direct method. Use backslash. Because it's a small system. It's going to be very efficient compared to anything else you're doing. So really what you should do is at the top of your function, first check the problem size. Like if A is an n by n matrix, you say, oh, if n is less than 100 or something like that, then just do this and exit. Otherwise, you do all this. Okay. So every recursive function should have an if statement like that. Check, like, is this a situation where recursion stops? You handle the simple case. Otherwise, no, we're going to do the full thing. Once this is done, you have this output E2H coming back to you. So what do you do now? You interpolate from error on the coarse grid to error on the fine grid. I will describe the interpolation process shortly. That goes hand in hand with the restriction process. Really, these two are opposites of each other. Recursion takes restriction. Restriction takes you from fine to coarse. Interpolation takes you from coarse to fine. Okay. So once you have it on the fine grid, then you correct your solution. UH is equal to itself plus the error that you just interpolated. And that's it. You're done. The function exits. Now the thing is, each time you go to a coarser grid, you're going from spacing h to spacing 2h, the number of grid points is cut in half. So let's suppose we start with, say, 1,024 grid points coming in. Then the next solve takes 512. Then the next one takes 256, 128, etc. If you add up all of those, all that work on smaller grids, that adds up to about 1024. So the computational expense of solving all of these systems on all the different grids adds up to only twice the effort it takes to solve on the largest grid. That's what makes multigrid so nice. That it's working with all these grids, but since each grid is smaller, it could do so very efficiently. Okay. So when you write this function, like for problem 6, this is how it will break down. So first you have this part that deals with the iterative method to produce the first approximation. Get your residual, do your restriction, recursion, you have your function call itself with the appropriate inputs to get the appropriate output. Work with the output, you do the interpolation, correction, that's it. The function is actually not very long because of how it's delegating to itself. Like I said, I do need to explain how to actually carry out interpolation and restriction. Are there any questions about other questions about what's up here? And there's certainly plenty of information in the hints document about this. Oh, I make a reference here to a video where I described the restriction interpolation. So that comment no longer applies, so I had to be careful about that. But I actually need to describe that right here. Okay. That's the only thing I have left to do. So it's a restriction. Let's show you an example of how it's done, how it can be done. There are many ways to do it, but this is what you'll use in the homework. Okay, so you have some vector, that can be residual, that's defined on a fine grid, and you want to multiply it by a matrix, what we call capital R. And for these matrices, the subscript will be the grid you're starting out on, so H. And there'll be a superscript of the grid you end up on. Okay. And the result of this will be a vector defined on coarser grid that has twice the spacing. So suppose that the length of this vector is 2 to the p minus 1. So for grid spacing of 2 to the minus p. Then the size of this vector would be 2 to the p minus 1 minus 1. So therefore, this has to be a matrix that has fewer rows than columns. So it's a short, wide matrix because it's mapping a longer vector to a shorter vector. Okay. So what this matrix does is it carries out averaging. So what it would do is, for instance, to get the value at the first point on the coarser grid, it's going to take a weighted average of the first 3 points. So here's the coarse grid, fine grid, and the coarse grid, and we're assuming the same problem we've been dealing with most of the time. It's usually boundary conditions. And then the coarse grid, so this would be like x1 tilde, x2 tilde. So what's going to happen is the value of your function at these 3 values contributes to the value here. So the value at the same point makes the greatest contribution. It gets twice the weight. But the points on either side make a contribution too. And then these 3 values are averaged, weighted average, to get the value at this, the second coarse grid point. So notice x3 is involved in both. That's why we have this here. 2 entries in the third column. So you form matrix, and this pattern just keeps on going. Okay. So you multiply your fine grid vector by this matrix, and you get a coarse grid vector that has these weighted averages. So questions about how this restriction process works? All right. Now, how do we go the other way? If we have a vector that's defined on this grid already, then how do we map these values to this finer grid? We have to fill things in. So that's where interpolation is called for. Okay. I don't feel like erasing this board, so I'll go to the other one. Well, still need a picture. And it turns out that it's easier to get than you might think. Okay. So now you have a vector defined on the coarse grid, in this multigrid algorithm is the error, and you want to multiply that by so-called I for interpolation. That maps from a grid of spacing 2h to a grid of spacing h. So notice the superscript and subscript are opposite what you have for restriction because it's going in the opposite direction. And that gives you a vector on the fine grid. Okay. So, so how this actually works is it's surprisingly simple. The interpolant matrix, all you have to do is take the restriction matrix that I just described, transpose it, multiplied by 2. Now, why does that actually work? So what happens is, so now we're on the coarse grid. Okay, and I'll need to write out at least the first few rows of this matrix. That's going to be tall and skinny. Okay, so what we have is the first row, we're just going to have a 1/2 for our first element. And then for the second row, we're going to have just a 1. And then we'll have 1/2 and 1/2. Okay, fourth row, we're going to have a 1. And then it keeps going, and so on. Okay. Now, so on the coarse grid, we have x1 tilde, x2 tilde. Okay. Now, so what happens is, notice that every other row has just a 1 in there. So these values are just copied to the same points. So it's trivial interpolation in that case. What's not trivial is getting these values. So for instance, the third point is the average of the first two. So these two are averaged to get this one. And that averaging happens at every point in between. What about the first point? It's just 1/2. So now that seems kind of odd. And so that's why part of it is not necessarily general purpose. So this right here works if the left boundary value is equal to 0. And like, so if we're doing like homogeneous Dirichlet boundary conditions, then that makes sense. Okay. Because then all you're doing is you're just doing linear interpolation between the value here and 0. So really, it's just, so you are averaging, you're just averaging with 0. If it is known that there's a non-zero boundary value at this point, then what you should do is add something onto this. Kind of like in problem 2C in the homework, where you're using second derivative of f, and f is non-zero on the boundary. So you have to add a correction vector to it. So then you can still have the same kind of averaging going, just with a correct value. All right. So all you got to do is form these matrices, and then interpolation and restriction are a snap. It's nothing more than matrix vector multiplication. So weighted averaging for restriction, and linear interpolation for this stage. You definitely want to form these as either sparse matrices, or you don't really form a matrices explicitly at all. You can just have a for loop that goes through the input vector and forms the output vector from one element at a time. Okay. All right. Oh, I'm just about out of time. Other questions? I know no one's near this problem, but you'll be there at some point. Okay. So I still have a little material left from chapter 4, and that is on Krylov subspace methods for that Ax equals B problems. So that is what I will cover on Thursday, virtually from the coast. I imagine we'll certainly have time for more questions then too. Okay. Guess you can all scram.
Hope you guys have an awesome Halloween.